Good evening or morning, depending on where you are. It's a pleasure to welcome Chris Conidis, who will talk to us about non-arithmetic algebraic constructions. Take it away, Chris.
All right, thanks, Linda. Thanks to the organizers for the invitation. Yeah, so today I want to talk a little bit about non-arithmetic algebraic constructions, some more complicated algebraic constructions than you typically see. So we'll get into that. So, some sort of, for me, this has become boilerplate at this point. So just some quick background on, where this all comes from. But in the 1930s, and even before that, people like Kronecker and van der Waerden, they studied what they began to study this field of computable algebra in the early 1900s, even in the late 1800s. And sort of once computability sort of came about, people like Turing and Post also studied computable algebra in the context of semi-group word problems. And so Turing and Post were able to show that for semi-groups, the word problem was undecidable. And then a little bit later on, people like Novikov and Boone showed the undecidability of the word problem, which is what Turing and Post were working on as well. And then a little bit later on, people started to sort of formalize this stuff and give formal definitions of computable fields and things like splitting algorithms. You can hear Russell talk about these sorts of things. That started with Froelich and Shepardson in the 50s. Then after that, there was things like Hilbert's 10th problems, maybe definitely one of the bigger achievements in the 1900s in this area. And then a little bit after that, in the 80s, computable ring theory sort of took off with people like Harvey Simpson and Harvey Friedman and Steve Simpson. Okay, so that sort of brings us up to date very quickly in a slide. And so what I mean by a computable ring is a computable subset of natural numbers equipped with computable binary operations for addition and multiplication. And all of my rings, I'm going to assume, have a 0 and a 1 element. And the other thing I should say is that all of my rings are going to be countable. I usually don't need to say that for this sort of audience. Okay, so just some basic background in ring theory before we sort of move on to the more computable ring theory. Remember that that an ideal in a ring, an ideal is called prime. If for any so we call an ideal P prime if for any two ideals A and B, we have that either A is included in P or B is included in P whenever the product A times B is included in P. This is a definition that works whether your ring is commutative or not. And I should say that for part of this talk, our rings will not be commutative. But we'll get into that. And so it's a fact that if your ring is commutative, what the previous definition amounts to is that an ideal is prime if whenever the product is in your ideal, then one of the individual factors is in your ideal. And if your ring is non-commutative, then we say that a two-sided ideal is prime if whenever the product ARB is a subset of P, then we have that either A or B is in our prime ideal. And one thing to note here, I think that most people recall from elementary algebra that that prime ideals are radical ideals. And so what that means is that if x to the power of n is in your prime ideal and you're in a commutative ring, then x is in your prime ideal. whenever a power of x is in your prime ideal, then x is in your prime ideal. If you have a commutative ring. But if you have a non-commutative ring, it is possible to have an element such that a power of it. Sorry, what am I? Yes. So it is possible in a non-commutative ring to have a nilpotent element, let's say, that's not in your prime ideal. And that comes right out of this definition here. And so if you're in a commutative ring, it automatically follows that all nilpotent elements have to be in every single prime ideal. However, if you're in a non-commutative ring, you could have an element x such that x squared is equal to 0. However, x is not in every single prime ideal. And that just comes out of this definition here, because that basically comes out of this criterion here. And so just keep in mind that that the intuition for non-commutative rings is different than for commutative rings in terms of which elements fall into every single prime ideal. We'll talk more about that as we go on. And so just some sort of background information. So back in the 80s, one of the first sort of achievements in this area is that Friedman, Simpson, and Smith showed that PA Turing degrees are essentially exactly what you need to find prime ideals inside of computable commutative rings. Right, and so they showed that if you have a computable ring, then every PA Turing degree computes some prime ideal, and also there is a computable commutative ring for which every prime ideal is exactly is a PA degree. Okay, so now I want to get into a little bit more algebra, and this goes back to what I was talking about earlier with these sort of nilpotent elements in commutative rings versus non-commutative rings. So if we're in a commutative ring here, so our ring is going to be commutative here, then we say that the intersection of all the prime ideals in a commutative ring, I'm going to call that the Nilradical of my ring. All right. And so it turns out that, let's see here, it turns out that the Nilradical of a commutative ring, which is just the intersection of all the primes, notice that this is a pi11 definition here, being the intersection of all the prime ideals. That's a pi11 definition of the Nilradical. There is a simpler construction of the Nilradical, which says that the Nilradical is basically the set of all nilpotent elements of your commutative ring, right? And this is where the name Nilradical comes from. And so you can characterize the Nilradical n as the set of elements such that there exists a natural number such that x to the power of that natural number is equal to 0 in your ring. So it's the set of all nilpotent elements that vanish when they're taken to a high enough power. And so this is a theorem of basic algebra. Most of us have seen this theorem in an elementary algebra course. And so the thing to note about this construction, the simpler construction here of the Nilradical, is that it's a sigma 0,1 definition of the Nilradical. And so with some elementary algebra, we have brought the construction of the Nilradical down from a pi11 to a sigma 0,1 construction. And if you sort of read through the paper of Friedman, Simpson, and Smith, they don't explicitly do this there, but they have all of the ingredients there. I'm not sure that they prove exactly this theorem, but there is a computable commutative ring for which the Nilradical is sigma 0,1 complete. It follows from things that are done by Friedman, Simpson, and Smith. pretty easily from that paper. So we have the Nilradical. It started off with a pi1,1 definition, but with some basic algebra, you can bring it down to sigma 0, 1. A similar sort of thing happens for something called the Jacobson radical. The Jacobson radical is the intersection of all maximal ideals of a ring. And in this case, it doesn't really matter actually whether you take a commutative ring or a non-commutative ring. The Jacobson radical, it starts off here as the intersection of all the maximal ideals, but you can prove, you know, using some basic algebra, you can give a pi02 definition of the Jacobson radical. And here it doesn't matter whether your rings are commutative or non-commutative. This pi02 definition applies in both cases. And is a theorem of Downey, Lemp, and Milletti that there is a computable commutative ring for which the Jacobson radical is pi02 complete. And so this pi02 definition is the optimal one for the Jacobson radical. Okay, and so now there's sort of one case that we haven't considered yet, and it's the one that I want to talk about for some time, a little bit of time. And that is, in a non-commutative ring, we can define something called, what I'm going to call the prime radical. Okay, and that's just the intersection of all prime ideals in a non-commutative ring. Okay, and this is a pi1,1 definition of the prime radical, similar to the one that we saw for the commutative case, but in the commutative case, you can show that the prime radical is equivalent to what we were calling the Nilradical earlier, and that was sigma 0, 1. But here I just have, in the non-commutative setting, I'm just going to start with this definition, the intersection of all the primes. And so, in order to get an alternative characterization of this prime radical here, I'm going to make another definition. So if R is a non-commutative ring and S is a non-empty subset of R, then I'm going to call S an M system. Okay, the M may stand for multiplication, I'm not sure, but S is called an M system if whenever any two elements are in our set S, then there exists some ring element such that the product, some ring element R, such that the product ARB is also in S. And so we have a sort of a closure property here. For any two elements that are in our M system, there is some ring element R such that ARB is also in the M system. So we have this sort of closure property here, and this closure property. One thing to sort of note about any sort of closure property, it allows you to generate subsets of your closed set. And so given A and B here, because a M system satisfies this sort of closure property, given any two elements in an M system, we can sort of generate using this closure property. We can always generate a subset of our closure, starting with any two elements A and B. I'm going to refer to this later on. This is why I'm sort of making a big deal about it now. I will refer to this at a later point where I want to generate a subset. And so now I want to connect up these M systems with the prime radical of our non-commutative ring. And so if R is a non-commutative ring, I'm going to let this script M here denote the set of all M systems containing some element X. And so this script M has a subscript X here. And this just denotes all the M systems which satisfy the closure property. So script M sub X is all the M systems containing some fixed element X. And then for any two-sided ideal I in our non-commutative ring R, we can define what in the non-commutative setting is called the radical of our ideal I. So here, I is a two-sided ideal, and I'm defining what's called the radical of I in the non-commutative setting, which is the set of X such that every M system containing X intersects our ideal I non-trivially, right? Or intersects our ideal I. And so this is what's called the radical of an ideal in the non-commutative setting. Note that this definition is also pi1,1, right? And so in the commutative setting, we started off with the definition of a prime radical, which was the intersection of all prime ideals in a commutative ring, and then using some elementary algebra, I said, well, the prime radical for a commutative ring is actually equal to this thing called the Nilradical, which is just the set of all nilpotent elements, and that was a story in the commutative setting. In the non-commutative setting, we can sort of generalize. We can do an analogous thing. However, this alternate characterization in the non-commutative setting is also pi1,1. It also turns out to be pi1,1, and so it is just as complicated as the thing that we started off, which sort of begs the question: is the prime radical actually pi1,1 or not in this case? So in the commutative setting, we were able to get it down to sigma 0,1. So keeping that question in mind, so here we are able to characterize the radical of an ideal I as the intersection of all the primes that contain our ideal I. And so here I'm taking the intersection of all the primes that contain our ideal I, and that turns out to be this radical here. And so this is the thing I was alluding to a little bit before. I was sort of, I got a little bit ahead of myself there, but so here, this is the corollary here, that that for a non-commutative ring, and so if you have a non-commutative ring and n denotes the prime radical, then n is just the radical of the ideal 0. All right, and this is and so n here is this letter n here represents the intersection of all the prime ideals, and then here we have the radical of 0. And so this is like saying that the prime radical is the set of all nilpotent elements in the commutative case, right? This is sort of the analogous theorem for non-commutative rings. However, we see that both sides of this equation are still pi1,1. Both sides of this equation are still pi1,1, whereas in the commutative setting, we had that the set of nilpotent elements was actually sigma 0,1. And so we were able to bring the complexity down via an algebraic and an alternate algebraic characterization of our prime radical. But here there is no such thing, because our definition of radical up above here is still pi1,1, and that's what I was trying to get at before. I sort of jumped the gun a little bit. And so we have this alternate characterization that's still pi1,1. So we're able to get the alternate characterization, but we aren't able to bring the complexity down like we were in the commutative case. And that begs the question at this point, just how complicated are these prime radicals? And so, just something to keep in mind, and this is more of an empirical fact, is that a majority of elementary algebra is arithmetical, right? It's hard to find algebraic theorems that involve non-arithmetical constructions. It can be done, you can find these things, For example, just something to keep in mind. I'm not, I'm not the, I don't claim to be like a super duper algebra expert or anything like that. But off the top of my head, I can't think of a single textbook that has more than one non-arithmetical theorem from algebra. That's just off the top of my head. Can't think of a textbook that has more than one in it. But that's just something to keep in mind. And so at this point, as I've been saying, we have two characterizations of the non-commutative prime radical, each of which at this point is pi 1, 1. So the question is just how complicated are these things in general? And so here's an old theorem at this point. So there is a computable ring R such that the prime radical of R is pi 1, 1 complete. Okay, and so you can push the complexity of these prime radicals up pretty high in the non-commutative setting. And so I just want to sketch the proof. And so the way that this sort of coding goes here is that we start with a computable tree in omega to the less than omega, such that every node of length 1 is in our tree. And so I'm going to use these angle brackets to denote nodes of length 1. And so all the nodes of length 1 are in our tree. However, the set of nodes of length 1 that are extendable to an infinite path, that set is pi 1, 1 complete. And so the nodes of length 1 essentially code a pi 1, 1 complete set, depending on which ones are extendable to an infinite path or not. So that's something to keep in mind. Every time I try to produce something in this talk that's pi 1, 1 complete, I am essentially going to code the pi 1, 1 complete set via these nodes of length 1, via these nodes of length 1. And so the way it works in the current context, where we have a non-commutative ring, and we're trying to show that we are trying to construct a computable non-commutative ring whose prime radical is pi 1, 1 complete. We start with we start with our sort of our base ring, sort of our universal ring here, which is the non-commutative ring. So keep in mind everything is non-commutative at this point. So it is the polynomial ring over the rationals, where the indeterminants x are indexed by the nodes in our tree.
All right, Chris, I'm missing something. Isn't that set sigma 1, 1?
Yes. Yeah.
I mean,
yes.
So you mean it's sigma 1, 1 complete?
Yes, I mean that it's sigma 1, 1 complete.
Okay, so yeah.
Yes. Yeah, I just about 10 minutes before the talk, I fixed another. I made the same mistake somewhere else. I fixed it there, but yeah. So this set here is sigma 1, 1 complete, and I'm going to do all my coding via these nodes of length 1. I'm going to do all of my important coding, I should say, essentially via these nodes of length 1. Okay, and so we get our polynomial ring here by just indexing our indeterminants by the nodes in our tree, right? And so we are in the end, we're going to be most interested in the indices that have length 1 here, but for now we just take them all. We just take them all for now. And the thing to keep in mind here is that our ring is non-commutative. And so the next thing I want to do, once I've taken, once I've done my indexing here, I want to define a function from my tree to this ring R naught here. And the way my function goes is I want to start by making the root, by mapping the root of my tree to the number 1, which is in my ring. And then for all the nodes sigma in my tree, I'm going to define f of sigma. I'm gonna send sigma to this product here, where sigma minus denotes the predecessor of sigma. And so this is an inductive definition, sort of going up the tree. If you imagine your trees growing up, then using f at the predecessor nodes, you get f at the successor node, sigma here. Okay, and so this is an inductive definition. So a couple of things to notice here is, I don't want to go into the proofs too much, but if you sort of look at this inductive definition, at no point are you ever going to see x sub sigma squared. If you look at this inductive definition here, at no point are you ever going to get a square. Maybe even before that, I should say that f sub sigma is always going to be a monomial. It's always going to be a product of indeterminates. It's going to be a product of indeterminates whose indices are taken from the tree T. And so this is a monomial, and f sub sigma is not going to involve any squares in it. And that has to do with the fact that our rings are non-commutative. I'm using the non-commutativity to get that fact. So we're never going to see a square here. We're never going to see a square. And the other thing is f sub sigma is going to, all of the indices that appear in f sub sigma, they're all going to be predecessors or initial segments of sigma, right? And so all of the indices are going to be comparable. They're all going to be comparable nodes in my tree. Those are just a couple things to keep in mind, right? So we're never going to see a square, and all the nodes, all of the indices in the monomial given by f of sigma, they're all going to be comparable going up the tree. And so now what I want to do is, once I have this function here, I'm going to use this function capital F to define the ideal that I'm going to quotient my ring R0 by. And so the ring I want, R, is going to be a quotient of the current ring R0. And so what I want to do now is I want to let I be the ideal, two-sided ideal, generated by the monomials that do not divide. So they don't divide any f sub sigma, f of sigma, where sigma is in our tree. All right, and so basically, if a monomial is going to survive in this quotient, which I'm going to take in a second here, the quotient here. So R is just going to be R0 modulo I. If any monomial is going to survive this quotient operation, it needs to be, in some sense, it needs to be saved by this function f, right? It needs to, it survives because it divides f of sigma for some sigma. And so if you're a monomial and you don't divide any f of sigma, then you become 0 in the quotient. Otherwise, you're sort of saved by one of these things here, and you survive in the quotient. Right, and so that's how this goes. And something I mentioned earlier is that this element here never has a square in it. This element here never has a square in it. And so according to this quotient here is basically saying that all the squares are killed in the quotient ring, right? And so every indeterminate x sub sigma is killed in this quotient here. right? And so that is just something to keep in mind, and it will give you a sort of an intuition for how the non-commutative case is different from the commutative case. Because if we were in the commutative case, the fact that all the that squares of all the indeterminants were equal to 0, that means that every indeterminate is nilpotent, which means that every indeterminate would be contained in the prime radical, the prime radical of a commutative ring, if our ring were commutative at this point. However, our ring is not commutative, and so something more complicated happens when we do this. That's not something more complicated happens that you know, it's not analogous to the commutative case here. So all the indeterminants, all of the individual indeterminants here become nilpotent. Their squares are equal to 0.
Chris, what do you mean by divisibility in a non-commutative ring?
So two-sided. So they is that what you're trying to get at, or is it?
Yeah, thanks.
Yeah. So divisible means two-sided. So it's yeah. So it's if you add a prefix and a suffix, you can
yeah, thanks.
Yeah. All right. And so now one thing to note, and I'm not, you know, it's not very hard to prove this, but the way that I constructed my F, one of the things, you know, one of the things I had in mind when I constructed this F in this particular way was this lemma here. So if you have an infinite path through this tree T, so keep in mind that the nodes of length 1 of T, those correspond to a sigma 1 complete set here. But the way that I constructed my function capital F was to make this lemma true here. And so if we have an infinite path F through the tree, then if you take just the union of the singleton monomial, so here we just have a singleton monomial, and so taking the union of just a series of monomials here, but the union of this series of monomials in my ring R is an M system that does not contain 0. All right, and that just goes back to the definition of M system. This is not a very hard lemma to prove. You know, it does require some care, but basically my definition of F was such that this lemma would be true. All right, and so a corollary here is that if you have a node of length 1 that is extendable to an infinite path, then there is an M system. There is an M system in our ring R containing x sub e here, where e is the node of length 1, but not 0. All right, and what this amounts to in terms of a previous characterization of the prime radical here is that x sub e, this indeterminate, would not be in the prime radical. It would not be in the prime radical, and this is from our characterization of the prime radical in terms of the radical of the 0 ideal, which is has a characterization in terms of these M systems. If you just unravel all of those definitions, this follows straight from definitions. There's no there's really nothing happening here other than a series of definitions. And so if you are extendable, if you're a node of length 1 that is extendable, then you can use an infinite path through the tree T to construct to basically show that this indeterminate is not in the prime radical by constructing an M system that basically shows that. Okay, and so this is sort of one half of the theorem. The other half is in the following lemma. If there is an M system, we'll call it A, containing 0, not containing 0, but containing some, we'll call it some polynomial element, the image of a polynomial in R, and if some indeterminate x sub sigma appears in the polynomial P, then it turns out there is an infinite, let's see, I think I mean to say a computable here, sorry. There is an infinite a computable finitely branching subtree above sigma, and basically the main point that I'm trying to get at here, the most important part, is that sigma is extendable. Sigma is an extendable node, and so if there's an M system not containing 0 and containing some polynomial in which the image of some indeterminate x sub sigma appears in the polynomial P, right? So you have some polynomial in your M system. It's a non-zero polynomial because your M system doesn't contain 0, and so it has to contain the image of some indeterminate x sub sigma. Then it turns out that sigma has to be an extendable node in the tree T. And the reason for that, just to give some intuition, so this is the harder half of the proof, but just to give some of the intuition, remember that these M systems satisfy this closure property, right? If A and B are in, then there is an R such that ARB is in the M system, and what this closure property allows you to do is, if you have P here and P is in the M system A, the closure property allows you to go from P to a subset of A just by reiterating the closure property again and again and again and again. Every time you iterate the closure property, sort of do it if you do it in the right way, which is also the sort of obvious way here, where you basically just keep using P sort of as much as possible. The degrees of those polynomials will get larger and larger and larger, and degree here, I mean the minimal degree of a monomial appearing in the polynomial. So basically, the degrees of everything are going to get larger and larger and larger and larger. However, as I mentioned earlier, there are no there are no squares in my ring, and there are no cubes in my ring, and there are no fourth powers in my ring. The squares of everything sort of die at that point, right? And so we have these monomials of larger and larger degree. The only way that can happen is if we have larger and larger products of sort of distinct comparable nodes, and those distinct comparable nodes, they essentially turn into this finitely branching tree. If you keep if you keep iterating the process of the if you keep iterating the closure property of the M system, the indices that appear in that sort of subset of the M system, those indices basically give you this finitely branching infinite tree above sigma. So I'm not sure if I said that's infinite. Yeah, there's an infinite tree, but that is true, and the closure property basically produces this tree T, is what I'm trying to say. And the finiteness property of polynomials, every polynomial is a finite sum of monomials, monomials over Q, and every monomial itself is a finite product. Those finite conditions give you this finitely branching tree. And that's just some intuition for how this lemma is proven. This is the harder half of the theorem. And so if you take this lemma along with the previous corollary here, basically putting it all together, we get that for every natural number E, the indeterminate x sub E, the indeterminate indexed by the length 1 node, E here, is not in the prime radical if and only if it's an extendable node. That's just putting everything together at this point. And so I've coded, I've basically coded my sigma 1 set into the prime radical via these indeterminants here of x sub E. I've basically done that, and that shows that implies that the prime radical is pi 1 complete via these indeterminants corresponding to nodes of length 1. Okay, so that is it's a rough sketch of how you construct a computable non-commutative ring with a prime radical that is pi 1 complete. That's a short sketch of how that goes. More recently, I became interested in another question of these sort of complicated algebraic constructions. And let's see here. Let's see. Yeah. Okay. Okay. So let's start with the definition. So this is also going to turn out to be one of these complicated things. So if R is now a commutative ring, so let R be a commutative ring. It can also be non-commutative, but it's more interesting that even in the commutative case, this thing turns out to be pi 1. So if R is a commutative ring and M is an R module, then we can define something called the radical of our module. We can define something called the radical of our module. And what the radical is it's the intersection of all the maximal, proper submodules. It's the intersection of all the maximal proper submodules, which also turns out to be the intersection. This is actually a non-trivial equivalence here. It is the intersection of all modules of the form P times M, where M is the module that we start with up here. M is just our big module, but P ranges over the maximal ideals of our ring, right? And so both of these characterizations of our module radical are pi 1. Okay, and this is a definition. You can find it in certain algebra books, right? And so this is how you define the radical of a module. I came across this question in a paper of Wu that asked for a characterization of the complexity of these module radicals. All right, and so I became interested in this because this is, I'd done something similar in the past. It looked like it was going to be pi 1, just looking at it, and it seemed like the sort of thing I should be able to answer. So I started thinking about this a few months ago, and so I was able to show that there is a computable commutative ring R along with a corresponding computable R module M, such that the radical of our module, which I defined on the previous slide, is pi 1 complete. All right, and one of the reasons I found this question interesting is because we're working with a commutative ring this time, working with a commutative ring, and so coding paths through trees in a non-commutative ring, just intuitively that sounds it sounds natural. You know, how are you going to code these things over a commutative ring? Of course, we also have a module, right? The module is going to do a lot of the lifting for us in this context. But the fact that we're working over a commutative ring, it got me interested. It got me interested. And so the proof is, well, I'm going to use the same tree T, because that's the only thing I really know how to do. So I'm going to use the same tree that we were just using, where the nodes of length 1 code are sigma 1 1 set. And I'm also going to pad my tree out with a set of computable leaves. And so in general, if you're working in omega to the less than omega, right, you don't know whether you're at a leaf or not in general. However, you can pad things out so that you know if you're at a leaf or not, just extending everything by a node of, extending everything by 1. Okay, and so in this case, so in the previous example, I was working over the rational numbers, and the rational numbers didn't really come into it at all in the previous theorem. For this theorem, I'm going to work over the algebraics. I'm going to work over the algebraic numbers. And if you've ever been to a talk by Russell, I mean, I don't know if he still says it lately, but around 10 years ago or so, if you ever went to a talk by Russell about 10 years ago, he mentions in a lot of his talks that if you have a algebraically closed field, I think it is of characteristic 0, then it automatically has a computable presentation, something like that, something close to that. And so we can work over the algebraic numbers or any algebraically closed field of characteristic 0, countable algebraic closed field. But we'll just work over the algebraic numbers here. Can anybody guess why I'm working over the algebraic numbers? Just as a little algebra type question. And so the reason why I'm working over the algebraic numbers here is because the main thing I'm going to work with is this characterization of the module radical here as the set of maximal ideals times the module, the intersection of maximal ideals times the module. And the only ring that I really know what the maximal ideals look like in general are polynomial rings over an algebraically closed field, right? And so if you're working with a polynomial ring over an algebraically closed field, the maximal ideals are just points. They're just points in sort of the space given by the set of indeterminants you have in your polynomials. And so we'll get into this a little bit later, but the point here is that maximal ideals are very well behaved if you're working over an algebraically closed field. And so that's why I'm working over this algebraically closed field. It's also, I work in computable algebra, and this is the first time I've ever really needed an algebraically closed field in what I've done. So here I'm making use of this algebraically closed field. And so I'm going to start by, I'm going to let my ring, so remember here, I need a ring, I also need a module. And my ring is basically going to be pretty straightforward. My ring is just going to be the polynomial ring with infinitely many indeterminants indexed by natural number over this algebraically closed field A. And now the thing to recall here, and this is where we get into, this is where we start thinking about maximal ideals. So pass through T, I'm going to think of as coding subsets of A. Okay, and these subsets of A correspond to, I should say, maybe instead of subsets, I should have said sequences. So a pass through T codes sequences of elements in A, maybe with repetition, and so these sequences of elements with multiplicity, they correspond to maximal ideals. Okay, and every maximal ideal over an algebraically closed field, every maximal ideal looks like this. This is what I was trying to get at earlier. Every maximal ideal basically corresponds to a point in this case, it's an infinite dimensional space because we have infinitely many indeterminants, but but every maximal ideal is generated by linear generators that look like this here, x sub n minus some field element here. And so the field element is going to be indexed, something to keep in mind. The field element is going to be indexed by the nth bit of our infinite path here, f, right? And so so f here, little f, denotes an infinite path through our tree T, or in general, a infinite path in bare space, right? So any infinite path in bare space, whether it's on our tree or not, any infinite path codes a maximal ideal in this way, right? Where the nth bit of our path codes the nth field element, the index of the nth field element in this in our fixed enumeration of our algebraically closed field A here. So the path gives a sequence of elements in our algebraically closed field, and that basically corresponds to a maximal ideal. And so the module, now we get to the module. The module is a little bit more complicated. The module here is generated by elements of the form x times m, and there's a lot of subscripts and superscripts going on here. And I don't know how much I don't know to what extent, how much detail I should go into here. But I see that I'm out of time anyway. But so there's a lot of subscripts and superscripts here. The superscripts I, so I can either be 0 or 1. I can either be 0 or 1. The sigma here corresponds to either a leaf in our tree, or else it corresponds to an element of length 1 in our tree. And it's the elements of length 1 where we're going to do a lot of the coding. But the leaves sort of tell us where we have infinite paths or don't have infinite paths. And somehow we're going to have to translate the leaf information back down to the nodes of length 1. And this is why sigma can be either a leaf or a node of length 1. And then k are some indices that run from 1 to the length of the leaf. So think of sigma as more being like a leaf than a node of length 1. And so this is the module. There's a lot going on in this module. The one thing I will say, so I'm out of time, so I'm not going to say too much more. The one thing I will say is that the main lesson I learned when I was doing this was that in order to get everything to work out over a commutative ring, so you know the trick here is that we're working over a commutative ring this time. In order to get things to work out here, I needed all of these indices. Is the point? Is the lesson I learned here? And so you can sort of the idea with all of these generators here is that the main thing going on here is that every node sigma gets its own sort of set of generators to work with, and that there's a lot going on in that statement I just said that I haven't gone into. I probably won't have enough time, but the main lesson I learned is that because you're working over a commutative ring, you need more indices to work with. You need more indices to work with, and the intuition here is that, just one last thing I'll say is that the intuition, so k runs from 1 up to the length of our node sigma, and this sigma comma k. Now you might be asking yourself, well, why didn't you just work with instead of having these two indices sigma and k, why not just work with the restriction of sigma to k? So just work with sort of the first k bits of sigma So the way I think of this generator here, this xm sub sigma of k, I do sort of think of it as a copy of a generator that that is indexed by sigma restricted to k. However, you want a different, the key thing is you want sort of a different set of generators for every single sigma. And I know, I doubt very many people understood what I just said in the last couple of minutes there, mostly because, you know, because I didn't really explain it well. But the main thing here is that to get things to work in the commutative setting, if you want to code sort of pi11 information in the commutative context, you need more indices, and you need to keep as much stuff separated as you possibly can. And I don't have time to go into all the details there, but the commutative case is a little bit different in that respect. And so here I say for each sigma, there is a certain subspace W sub sigma that is separate from every other W sub tau. And so you end up, for every sigma as a leaf, you end up with this R invariant subspace W sub sigma. And one of the key things is that every node gets its own subspace. So they're all sort of infinite dimensional, but they're all separated from each other, and that helps when you're working over a commutative ring. Okay, I will stop there, and so if anybody has any questions or anything, feel free to ask. Yeah.
Thank you so much, Chris, for giving us this nice talk, and so late at night for you as well. What questions do we have?
I have a quick question about the definition of your a capital I. When you take R0 and R, one was the quotient of the other. Why is it easy to see that I is computable, because you need that, right, in order to make
Yes, you need that. Yeah, I ignored that. Yeah.
But that's probably a fairly easy check. I mean,
at the level of monomials, right? At the level of monomials, it's kind of easy. Like if I give you if you have a monomial, checking whether that monomial divides some. So first of all, if you have a monomial, as I said earlier, in order for that monomial to not be an I, all the nodes have to be comparable, right?
okay.
And so if you have something that has incomparable nodes, you know, right?
Okay.
And so because now all the nodes are comparable, it's going to have a maximal. It's going to have a maximal node, right? And you can use that sort of logic to get a bound on which sigmas you need to actually look at, right?
Okay.
And, yeah, that's how the proof of that goes. Yeah.
So when you have one of these, so new question. So when you have one of these prime radicals that is pi11, if you think of it as a union of simpler sets, sigma alpha sets for the various alpha according to how difficult it is to see that some x enters. Is there a way to do that is also sort of means something natural from the algebraic perspective?
I see. Maybe there might be for this particular ring. Yeah, I'm guessing. I don't know for sure, but it might have something to do with degree or something like it's. I see. I'm not sure. So it's, yeah. So the tree is sort of coding these M system type things. So it would a natural characterization will just say it would be in terms of these M systems, and it might be something. I'm not sure exactly, but it's like, because it's sort of like where you I see. Yeah, I don't know. Now I'm thinking about it. It's an interesting type question, but yeah, I can't express it. Can't express it algebraically necessarily. It is an interesting question, though. Yeah, I never. Yeah. Yeah, I don't have a good answer for you. But it's like it's kind of related to like when your M system hits 0, when you're if you're or like where you're. Yeah. No, I don't know.
I don't know as well, obviously.
Yeah.
So,
Yeah.
So yeah. What other questions do we have?
Chris, I wanted to ask, so this ring R, is it going to be in the Theorem?
It's ring R for
not R0, but R, like the quotient, yeah.
no, because the indeterminates should all still be independent.
Right, okay. So,
yeah,
so then the follow-up question is it possible to have an Theorem ring which has this property, this completeness property?
Yeah. I don't. So you mean like a left Noetherian ring, or?
Right, like left or right or both. I'm not sure,
Yeah.
but
Yeah.
yeah. I mean, I don't know. This seems like a question that might actually be relevant for algebra, right? Because maybe in Noetherian rings there's an easier characterization of this this object. But maybe not, and in which case you can prove that there is none.
So that's what's really going on, is what you're trying to say. Yeah. A lot of the rings a lot of the rings I've coded into in the past have been non-Noetherian.
Right. Right. That's why I asked this question.
Yeah. No, that's an interesting question. Yeah.
No, thanks.
Yeah.
All right. Well, let's thank Chris again. Thank you so much, Chris.
All right. Thanks, everybody.